Okay, so in this footnote, we're going to be discussing about slime girls. And I got the motivation to make this video because of a short that I saw from Professor Lando. Um, so universe bless his soul, um, where he talked about slime girls. So it wasn't a very long short. I mean, it's short. It's a YouTube short after all. Um, but nonetheless, he talked about slime girls in it, and so I thought to myself, oh, how about okay, like what if we considered in the last lecture a mass, a shell-like mass with some fluid, right? Some fluid that composes it, right? And it has some density, energy density, right? So what if I consider this time a solid ball of matter, not metal, of matter created out of slime? So the main premise of this video works on the assumption that slime girls are very flexible to the point wherein they can turn themselves into a spherically symmetric mass. So I have my slime girl. So for example, maybe Sue or other people, most notably Sue from Monster Musume, because we've seen her transform into a sphere-like object. So this metric or this discussion works on the basis that slime girls can turn into a spherically symmetric mass. I'm gonna call her green because slime is usually in the color green. So it's a simple to derive the metric for this type of situation, these special cases, is just a simple modification of the Deliro or Carnero metric that we discussed in the last lecture. So if you have not seen that yet, I highly suggest you guys watch the last lecture. So so right before we discuss or continue the discussion, I want to first state a thing about the R coordinate, this RG that I kept mentioning back then. I just say it was the R coordinate, but it's literally an R coordinate or the coordinate of some point on the sphere that you're considering. So RG is literally R1 from the last lecture, okay? So it's literally the radius. So instead of R1 or R2 that I discussed in the last lecture, we're going to be considering only one value, RG, which is literally the radius of the sphere your slime girl turns into. Now I want to emphasize that this metric is very broad when we formulate it. This new metric of concerning slime girls, okay, it's going to be very broad because the density of slime girls it varies from slime girl to slime girl, and right now it will also vary with their mass. So if for example your slime girl eats a lot of food, right, they gain mass and energy, so their energy density increases, so it will vary, right, for each slime girl. And of course each slime girl is different. No two slime girls are the same. Even if they can morph into each other, some would have a different mass than others, right? But really all you need is mass and the specific radius that they turn themselves into when they turn into, or the radius of the ball that they turn themselves into. So sometimes maybe your slime girl has few mass, but when she morphs into a spherically symmetric mass, a ball, it's a big ball, right? She can distribute her matter or her slime matter in a way wherein she can achieve that big size but have small mass, right? So yeah. So it's a simple matter of tweaking the initial conditions we had from for when discussing the Deliro Orsello Cornero metric. So what we change is our rho of R. So this time, instead of 3 components, we only have 2 components, because what we're doing is essentially shrinking the inner shell, the inner sphere that bounds that quote-unquote shell into nothingness. So we only have one sphere that bounds the mass, which is your slime girl. So P of R is this time rho naught for some 0 or some value R greater than 0 but less than RG, and 0 for an R greater than RG, where RG is literally the radius of the ball your slime girl has turned into. This is RG. Okay, and then the pressure stays the same thing. It's still 0. There's no pressure acting on it. Okay. So the pressure, except we just eliminate one component of the piecewise function. So it's 0 for r equals r2 or rg, and 0, still 0 for some r greater than rg. Okay. So that's my initial conditions. Alright. So the reason why we were concerned with r mu in the last video or the last lecture is because we had a mass, right? We had a mass that's a shell-like, and there will be some concentration of energy in the middle, in the inside of that shell. But now that there is no inside of the shell per se, we're only focused with the Schwarzschild radius of our object and see whether its current radius rg keeps up with that Schwarzschild radius, and so see if our slime girls will turn into a black hole. So even if your slime girl can sort of morph into however radius they want to, right, into a ball of however radius they want to stretch, there is a theoretical limit wherein they cannot stretch under. So there is a theoretical radius or value wherein their radius cannot go under unless they want to turn into a black hole and essentially die in the process. So recall that the line element d squared for this type of mass, which is spherically symmetric mass, is x of 2 nu of r c squared dt squared. So I'm gonna use the plus ones minus convention. So minus x of 2 lambda of r squared minus r squared g omega, wherein again g omega is the standard metric on the 2 sphere. And so take into consideration these initial conditions, our nu of r works out to be the following. So because we eliminated one component of our boundary conditions, we only need to concentrate on two regions now, or two components. The component that concerns the region of space inside the body of your cat girl, and the region of space outside your cat girl, or around your slime girl. Sorry, getting my knickers twisted. Okay, so it's minus 1/2 ln. Same thing. We just eliminated the top component. So minus 1/2 ln of kappa rho naught times rg cubed minus r cubed plus 3 times r minus rs all over 3r for some 0 less than equal to r less than equal to rg. And the second component, which so happens to devolve into the exterior Schwarzschild metric, is minus 1/2 ln r minus rs over r, and that's for any r or any point r outside of my slime girl. And then our lambda of r is pretty much the same thing, except we eliminate the first component. So this 1/2 ln of rg minus rs over r for some r greater than rg. And then this is 1/2 ln now 1/2 ln rg. No, I need to erase this. Sorry, it's not rg, it's just r. So it's r minus rs over r. Okay. And for here, it's rg minus rs over rg. And then of course there's that plus the ln of that one integral z of r for some r hemmed between or inside the body of your slime girl. So from 0 to rg. So the same values that we use inside the z of r integral is the same thing, except I just change a variable or two. Okay, so gamma naught squared is still kappa rho naught, and p of r is still equal to capital P of r over rho naught, and our z of r is this, to the square root of gamma naught squared times rg cubed minus r cubed plus 3 of r minus rs all over r times the square root of rg over 3 times rg minus rs plus 3 over 2 times the integral running from rg to r ds. So with respect to s of gamma naught squared s to the 5 over 2 over quantity gamma naught squared rg cubed minus s cubed plus 3 times s minus r s. So the Schwarzschild radius of your slime girl, 3 over 2, and then quantity, and then just close the brace. Okay, so what about the density, the energy density rho naught of your slime girl? Well, that depends on the mass of your slime girl, whether your slime girl is thick or not, or whether they eat a lot or not. But to find the energy density is actually quite simple. All you have to do is use the formula E squared equals m squared c to the fourth plus p squared c squared. And that is if your slime girl is moving. And considering that the Earth or whatever planet you live on is moving around a certain star, you're technically moving. So there is some momentum. But you could assume with relative ease that E equals mc squared. And from there, since this gives me my energy density, to get the energy density, I just need to divide by the volume of my slime girl. And conveniently, the reason why I wanted to discuss this is because we know the volume of a ball or of a sphere, and the volume is precisely 4 over 3 pi r cubed. So when you've measured the radius of your slime girl turned into slime ball, right? And you know her mass, it's easy to derive the energy density. So my rho naught will be precisely 3 over 4 pi r cubed, and then that's times E equals mc squared. So mc squared. So this is precisely 3 mc squared over 4 pi r cubed. I'm going to use a capital R to denote the radius. Or in terms of that r coordinate, I'm going to say that rho naught is equal to 3 mc squared over 4 pi rg cubed. So this is the key formula in finding the energy density of your slime girl. So again, it will vary from one slime girl to another what exactly their energy density is, depending on the mass and the radius for which they turn themselves into. But a warning, just a warning to your local slime girl. There is a certain theoretical value based on their mass and, just their mass, to be honest. Wherein if they turn into a ball, they cannot shrink, absolutely cannot shrink, below. And that's precisely the Schwarzschild radius, RS, which is 2gm over c to the fourth. So here's the thing, RG must be strictly greater than RS. unless your slime girl was to die. So yeah, it's the third key thing. So this is our, in summary, this metric here gives us the region of space-time inside your slime girl and outside your slime girl, who has turned into a spherical ball of slimy mass. So depending on what type of slime your slime girl is made out of, the energy density will be different. And the energy density is given by 3mc squared over 4 pi rg cubed, wherein rg is the radius of that ball that your slime girl's turned into, and m is her mass. And I must emphasize that if your slime girl does decide to turn into a spherically symmetric mass, that they absolutely cannot shrink to 2gm over c to the fourth, which is their Schwarzschild radius. I'm gonna write it in terms of the m in the last equation. So there. So Rg is strictly greater than Rs unless they want to die. So prevent them from shrinking below that. So this is just a short footnote. I just thought of doing this because I saw that one short by Professor Lando. Please subscribe to him, because honestly, LOSC would not have been possible without him, because he was the one who gave me the inspiration to start all these enterprises. So give him a subscribe or check him out. Or maybe you've seen his videos and you saw mine afterwards. I just want to give a huge thank you to him, okay? So kind of please notice me, Professor Lando. When are we going to do a collab? So that'll be it for this footnote.